Good evening. Welcome to the East Midlands Centre of the Royal Meteorological Society. My name is Professor Michael Stephen. I'm chairman of the East Midlands Centre, and we run a number of meetings like this every year. The Society's mission is to strengthen the science of weather and climate and to raise public awareness of atmospheric science. The local centres, such as the East Midlands, exist to bring the Society to its members in the region and to broaden interest among the public at large. We also try, when appropriate, to promote local expertise in atmospheric science. I have a few housekeeping items to mention. We encourage you to answer questions, ask questions of the speaker. If we could have the next slide, please. At the end of the presentation. And the way to do this is to click on the Q&A button on your screen and to type in your question. You can do this at any time. The questions are then collated and I will read out a selection at the end. We also encourage you to engage further with the Royal Meteorological Society. You can sign up for a general online interest newsletter called Met Matters, which is entirely free. Or for even deeper engagement, you can join the Society. Unfortunately, that's not free. For further details on any of this, see the Royal Meteorological Society website, rmets.org. Tonight's speaker is Dr. Massimo Bollasina from the University of Edinburgh, where he is a reader in atmospheric science. His research focuses on mechanisms of climate change and variability at the regional scale, including atmospheric aerosols and atmospheric teleconnections using global climate models and observation. He studied physics in Milan and later moved to the US as a scientist at the University of California. He completed a PhD in atmospheric and oceanic sciences at the University of Maryland, and then worked for NOAA Geophysical Fluid Dynamic Laboratory at Princeton. He finally reached Edinburgh and is now a reader where he conducts research, supervises students and postdocs, and collaborates with international research institutes. And now I hand you over to Dr. Bollasina to give his talk. Thank you.
Hopefully, everything should be in place. Can you confirm, Michael?
Yes, it's in place.
Okay. So thanks everyone for joining this talk, and especially thanks to the Royal Meteorological Society for inviting me, and Michael in particular for keeping up and sending me several emails and invitation and so on. So thank you very much. I really appreciate this opportunity. So we are going to talk today about climate models and as models as tool to predict future climate variations and change. And this talk is, of course, contained in 45 minutes or so. So I'll touch upon various aspects of climate modeling. It's not comprehensive, the talk. I touch several aspects, but of course is not exhaustive. There are many more aspects that one could talk about. And just to start, setting the stage, these two, one is in animation and the other one is a picture, are actually representations of the output from state-of-the-art high-resolution climate models. And of course, we don't know the details of that particular day or year or month, but we realize that we see immediately that these pictures are very realistic. In particular, you see in the animation on the left, the formation of ocean eddies off the eastern coast of the US, which is actually quite a nice improvement, a substantial improvement in climate modeling, oceanic modeling. But I also found very fascinating and very interesting, actually, to see and to follow how models developed over time, over basically the last 60, 70 years. And this quote is from Richardson, who attempted the first weather forecast, and I'll talk about in a moment, and who actually thought that perhaps one day it would be possible to advance computation faster than the weather advances. But that is a dream. So to have forecasts that actually are useful. And that is just about a century ago. So what is a climate model? A climate model is a mathematical representation of the climate system based on physical, biological, and chemical principles. And we'll talk about these later on in the talk. So first of all, we talk about climate model. I should more properly talk about Earth system models. But when we talk about the climate modeling or Earth system modeling, we have to have in mind how the climate system works, which is essentially composed of 5 main components: the atmosphere, the land, the ocean, the ice, and the biosphere, and the human component. So actually 6. And how these components and their own features are tightly linked together, and changes in one of the components, in one of the processes, affects many others, even in other components apparently separated from the one that is being perturbed. And a deeper understanding of how the system works demands quantitative understanding, which can be realized only through climate models. But when we talk about the climate system is not static. It is composed of a number of features, phenomena that occur over a large range of spatial and temporal scales. We go from the micro scale, where turbulence is, and up to the largest scale of climate variations, where changes occur over a time scale of a century or 50 years or so, over spatial scales of thousands of kilometers. In between, we have a lot of features and phenomena that we heard about. We know some of them, and across scales. And what's important to notice here is that they're all interconnected. And so it's important. A climate model is not necessarily scale selective. So in principle, a model can represent all these features as it is being executed on a computer. And also, this picture here shows key components in terms of response time. When we talk about climate modeling, we also have these major components, but each of them is more active over a certain time scale. If we think of the atmosphere, of course, we know the atmosphere moves very fast. And if we have a perturbation to the atmosphere, it can propagate around the globe in about a month. Of course, on the other side, you understand that if we perturb the deep ocean, it can take a century or even longer to adjust and to adjust. It's just simply to adjust. And then we have a range of other scales depending on the component that we consider. So this is just to give an overall perspective. A model also includes all these interactions here. As I said, I found fascinating to look a little bit at how climate model develop. And it's one of the great triumphs of the past 70 years. And models are essentially a key tool for us to predict future climate. And yet, it's interesting to know that probably most of you know already that numerical weather forecasting actually started more than a century ago, and long before the first electronic computers were actually operative. But yet, in order to make numerical prediction successful or effective, there was, although forecasting, actually, the basic ideas of forecasting were developed a century ago, there were some other tools or knowledge that needed to be developed: a better understanding of atmospheric dynamics, So which equations govern atmospheric motion, observations of the free atmosphere in order to initialize weather models and then climate models and so on, development of numerical schemes in order to adapt, to make these equations work on computers, and then, of course, availability of computers. And many says that climate weather and climate forecasting and predictions developed together with computing, and this is indeed true to some extent. So the pioneers of weather forecasting essentially are three people. Cleveland Abbey, an American meteorologist who first identified that the use and recognized the use of hydrodynamics and thermodynamics to understand meteorology. Bjerknes, a Norwegian scientist, actually developed formally and rigorously the equations that can be used in atmospheric science and in meteorology. So it was really an exact development of these equations. And finally, Richardson, a mathematician who carried out the first forecast, attempted a solution to these equations of motion. It took him 2 years to develop this forecast by hand. And this is an interesting story here, because we often heard about the fact that the forecast, which is shown here on the top left table, you see LFR is his forecast, and with the surface pressure, and you see that the surface pressure actually developed to up to a change of 145 hectopascal, which is unrealistic, obviously. Mod is the calculation made by a computer, and you see that the computer actually gives the same solution as he obtained, is within a decimal. DFI is actually a refined solution with a computer, but filtering the initial data. As you see, pressure converges to a certain deviation, which is reasonable, 0.9 hectopascal for a 6-hour forecast. What does this mean? It means that actually the error, the problem that led him to this overestimation of the pressure change was actually not in the calculation per se, but was actually in the initial data that were provided. So this emphasizes the importance of knowing the initial conditions well for a successful weather forecast. As we know it now. At that time, 100 years ago, was less known. And Richardson imagined, in a way, a sort of depiction of how he saw forecast was this sort of forecast factory, where there were 64,000 people communicating, solving the equations at each grid point, and then communicating with papers the results of their computation to the neighbor people, and with a beam of light scrolling through the people and making sure they were working at the same speed. So this is so-called Richardson forecast factory. Then the first computer came called ENIAC, and which was actually initially commissioned by the US Army to calculate the dynamics of projectiles. And this was a gigantic machine consuming 140 kilowatt of power. And the computer, which is quite a lot, was really a large room. And the coding in the early computers as well was through these cards here that were actually punched by hand. So this is how actually earlier programming was done. Moving slightly later, this is the when weather and climate computing actually developed massively. John von Neumann, an American and Hungarian mathematician, sort of had a vision, in a way, in which he saw that actually meteorology and weather forecasting was perfect to be developed on these supercomputers. And there was the first project of meteorology, which started in Princeton in 1947 and was led by Jules Charney, which probably many of you have heard about. And there was the first a 24-hour forecast with a computer in 1950. The picture down shows John von Neumann. And a few years later, in 1954 in Maryland, there was the development of the Joint Numerical Weather Prediction Unit. And this is the picture of the first, the map of the first prediction. One of these, they're almost basically indistinguishable. This is the mid-troposphere geopotential height, 500 hectopascal. One is the forecast, and one is the observations. And you see on the left is the domain used by the model. Each is very coarse. You see basically 15 by 13 points. And it took 24 hours for a 24 hours forecast. And interestingly, the same forecast was recently implemented on a phone. And it's called Phoniac. And you see here the result of the forecast, which is very similar to what we saw before. And this simply attests for the massive amount of computational resources that have occurred basically in the last 70, 80 years, 50, 60 years or so. What was achieved at the time on a supercomputer is now achievable on a smartphone. And this links to the so-called Moore's law, which is not a law, but is basically an observation. Moore stated that every 2 years, the number of transistors double. And this is indeed has been occurring over the last decades. You see, the peak speed of supercomputers have doubled basically every 2 years to have this linear increase. Notice that the scale on the left is logarithmic. This is why we have a line. And this is true, although recently there are some limitations. Transistors cannot become smaller and smaller. There is a limitation also in how heat is being dispersed by these transistors. So, and also the scale of the transistors cannot become smaller and smaller to fit on the same place, smaller than an atom, obviously. So there is a limitation. So we are reaching really a saturation in this curve. And climate modeling, proper climate modeling developed even further in Princeton under Norman Phillips, who did the first long range. This is the first long range general atmospheric circulation simulation, and with multiple layers in the atmosphere. And under this effort, there was a very influential workshop conference in Princeton under John von Neumann again, application of numerical integration techniques to the problem of general circulation. So he envisioned really that we should push forward the simulation of climate, general climate, and he actually started raising interest in meteorology and in climate modeling. And as such, several modeling groups developed soon after, and the modeling groups are 4 in the US, and one in a bit 10 years later in the UK, the UK Met Office. The four modeling groups in the US are, of course, GFDL, the Geophysical Fluid Dynamics Laboratory, and at NCAR, the National Center for Atmospheric Research, and UCLA, the University of California at Los Angeles. And it's interesting to notice here that the leaders of these 3 groups were one American scientist and one Japanese scientist, Manabe, Arakawa, and Kasahara. And each of the 3 scientists with their own set of skills, all 3 coming from Tokyo. And each of the groups actually contributed differently to climate modeling. As you see here, for example, Smagorinsky and Manabe, GFDL, was the first model with 9 layers, while the previous ones were actually 2 layers only, and so on. There was another effort at the Lawrence Livermore National Lab. Was an individual model, individual effort by Leith, and then the UK Met Office with the first operational model in 1965 and the GCM climate model in 1973. And this is Manabe in his office at GFDL with Smagorinsky. And in this picture on the left, the bottom picture, there is also Kirk Bryan, who actually was the first to implement an oceanic model. Initially, the models were just atmosphere models. And you see here an equation from Manabe from his work, actually on the Paris Underground Station, which was on display a few years ago. And a picture from his famous paper that actually awarded him the Nobel Prize a few years ago. He was the man who predicted climate change. He perturbed atmospheric concentration of CO2 and actually got the result that actually under doubling CO2, the world will warm by, with relative humidity fixed, will warm by about 2 degrees. And this is the profile of temperature. He also saw here the atmospheric cooling in the troposphere, but also the stratospheric, atmospheric warming in the troposphere, but stratospheric cooling, which is what we see now. And his estimate, after all, is not so different with what we see today. Today, climate sensitivity, so the temperature change, global temperature change in response to a doubling CO2 varies between 1.5 to 4 or 5 degrees. So his estimate was within the plausible range that we see today. And if we talk about climate modeling, of course, models develop, but they were all, why did we talk about CO2? So climate modeling is also necessarily related to the, if you will, the discoveries of the effect of CO2 on CO2. And so the greenhouse effect was first identified by Tyndall in 1850, who already understood that the atmosphere will warm under CO2. So CO2, so greenhouse gases and CO2 in particular are responsible for warming the atmosphere. Then Arrhenius was actually the first who calculated the effect of doubling CO2 with estimates that, again, are not very different from the ones that we see today. Calculate the effect of changing CO2 on the temperature. Of course, not with models, but with instruments. We mentioned already Bjerknes, who formulated the primitive equations. Richardson, the first forecast. And then we also reach a calendar who actually measured for first global warming and looking at time series and looked again and correlated the amount of warming to the amount of CO2. Then also there were other scientists. We saw the history of modeling and computing, and Revel was actually pointed out in 1949 the importance of oceanic mixing and the fact that it can limit, to some extent, limit the absorption of CO2 from the atmosphere. So CO2 remains largely in the atmosphere. Keeling, Charles Keeling, made the first long-term measurements of CO2 in the observatory and established the observatory in the Hawaii. And we actually now we have a long time series from 1959 to present day of CO2, and we see clearly a lot of features that appear in the climate record associated with the changes in CO2 measured there. And the observatory is a very in a very nice position because it's isolated from contamination from cities and direct human activities. Charney report is a famous milestone in 1979, was received the task by the National Academy to do a review and review and stated that equilibrium climate sensitivity, so the warming associated with doubling CO2, reached 3 degrees Celsius. Then in 1988, IPCC, the Intergovernmental Panel on Climate Change, formed, and then later on in 1992, the United Nations Framework for Climate Change, so an initiative to combat climate change, formed as well, and so on, and the various efforts to study and project climate change started with the so-called couple model intercomparison projects. So going back to a model, and we'll touch upon this aspect in a moment. So a model, we said, is a representation of a phenomenon of interest. In this case, can be climate, but models might not be we might not need comprehensive models for climate. We could well also use more simplified models. Why do we use climate models, though? Obviously, the first objective is to project the future, but we can also use models to carry out what-if experiments to study the sensitivity of the climate or of a certain phenomenon, not necessarily climate, it's a climate feature, to, for example, changes in the orography. And actually, one of the first papers by Banabi was actually the influence of orography on the global atmospheric circulation. And so this kind of experiments that help understanding what a certain features, why certain features is important for climate, and also to understand why a certain phenomenon occurs. This is more related to observations. Is the model able to explain observations? Can we get insights into the mechanisms that drive this observational phenomenon? Why does this occur? So all these kind of applications can be done with a climate model. Important components of a sophisticated climate models are essentially four physical components, and one is more computational. We know that the engine of climate is radiation, how much radiation comes in on the Earth and how much is emitted. So a climate model needs to have a radiation component. Radiation in a realistic model has to disperse, and the energy needs to be dispersed, for example, between the equator and the poles. So you need dynamics that controls the movement of energy. Of course, energy is also absorbed by the surface, can be the ocean, can be the ice, can be the land. So we need a land surface model and energy fluxes between the two components in the vertical and horizontal. Then chemistry. We need chemistry because the air contains a certain components, including greenhouse gases and including CO2. So a sophisticated model needs to account also for this. And then the fifth aspect is related to how this model needs to run, so space and time resolution, because this is how we resolve models on a computer, and we will see in a sec. But based on what I said, models do not need to be sophisticated. Even the simpler models are actually very helpful. A simpler model is a 0D energy balance model, basically representing the Earth as a point. And we know how much energy is coming in from the sun. We know how much is emitted. This is 0D because does not consider the atmosphere. It's simply balanced, and the Earth is basically simulated by one point, one layer, without vertical layers. 1D models is energy balance models, the one that follows, is indeed using also a vertical profile, typically 2 or more layers, to account for the atmosphere and the fact that energy or solar radiation and outgoing long-wave radiation is being absorbed and dissipated through the layers. And a more sophisticated model also includes some kind of convective adjustment. So the fact that if you have also humidity, if you reach a certain level of saturation, humidity condenses and the atmosphere adjusts back to the initial profile, and so on. And then you go into GCM, so-called general circulation models, which are not 1D, they are 3D, are 4D actually, because they have also time. Before going that, there are also the so-called intermediate complexity models that are, for example, two-dimensional EDMs, when you consider also latitude. The fact that radiation received from the sun is not uniform over the surface of the Earth, but depends on latitude. And then there is also transport across latitudinal bands. And then again, we go towards complicated GCMs, can only be atmospheric only, keeping the ocean fixed, can be regional models, can be fully coupled atmosphere, ocean, general circulation models, to the state-of-the-art now models, which are Earth system models, which they include, are more sophisticated in that they include interactive vegetation, in fully interactive carbon cycle, so carbon can go through the vegetation, is being absorbed by the ocean, is being emitted, and biogeochemistry. So these are really Earth system models. How are models solved? We solve equations based on discretizing the atmosphere, the ocean, and so on in grid boxes, and calculating the balance of a certain quantity across the the size of this box. A certain amount goes in, a certain amount goes out, plus there are sources and sinks within the box. And essentially, this is how we solve the equation, by solving for the fluxes and the local tendency within the box. We solve this for each grid box in space. And for example, to give an idea of how the equations look, they look like this one here. This is the equation for density, for mass, sorry. Rho is density, is mass per unit volume. So this is the local tendency. On the left is the change per unit time, and the expression on the right is the flux. V is the wind, and so density, mass is transported by the wind, and the operator calculates the convergence or divergence in a box, okay? And at the core of the equations of the climate model, weather model, is the Navier-Stokes equation. And if you want, I'm not here to discuss this, of course, it's beyond the scope of this talk, but the equations are like this. You don't have to look at these equations. It's basically balanced equations for key variables of temperature, pressure, winds, and humidity. These are the equations that are being solved in a model. In the left boxes are tendencies. These equations are prognostic. So variations of a certain quantity in time as a function of a number of sources and sinks on the right. Notice one thing, the equations are coupled, which is quite a challenge. It's not an equation for temperature that does not depend on wind, and the equation of wind, of course, depends on temperature, so are a two-way coupled. Okay, this makes the system relatively more difficult to solve. As I said, equations are solved on individual grid cells over the globe, in the vertical and the horizontal, calculating fluxes among them, and this in the ocean as well. And each box communicates with the one neighbors and with the one above and on top, and so on, so essentially. And at the bottom, we have boundary conditions, like, for example, orography, like the land, surface, and so on. And the land model is the same. You have exchanges across the various components of the surface. Okay, this is how models are solved. And just to give an idea, you can imagine that you have a number of grid cells here, grid boxes, and of course, in each of these boxes, we need to solve the same number of equations. Each equation has a certain number of operations to be done. Plus, you need to multiply by the number. Each of these equations need to be solved in finite time steps. So you need to multiply then for the number of time steps for the full, to calculate the full computational time of a simulation. And also, you might say, I increase the resolution. Yes, I can increase the resolution, which means increasing or halving the size of the grid boxes, which means doubling the number of grid boxes in one direction, which means it increases by 4, because it's also both direction in the horizontal. Then you have to account also for the vertical resolution. And there are some conditions in the numerical integrations of these equations that if you double the resolution horizontal, you need to halve the time step, because essentially the propagation of waves needs to be resolved. If the box is too small, you need to solve the equation more frequently. Otherwise, the wave is not solved as it propagates through the boxes and the model diverges. As a matter of fact, so there is a compensation between the horizontal resolution and the number of time steps that you need to integrate the equations for. So the number of times you need to go through the same loop to solve the equation. So this is all contributes to the so-called throughput of a climate model. To give an idea of sort of state-of-the-art models, this is taken from NCAR, a modeling center that I mentioned you before. This is the throughput of a number of models, depending on the resolution, depending on the number of points, depending on the characteristics of these models. The resolutions here is typically given in number of years per real time, so per day. And you see it goes between 1 year, 2 years to 15 years. This is typical resolution of climate models now. So we can simulate typically 10, 20 years of climate in 1 day. To do that, we need supercomputers. And these are the pictures of the most famous supercomputers in the world. The Metophis, the NCAR, Cheyenne, the NCAR Archer 2 here in Edinburgh and in the UK. And this is how it looked like when it was mounted, assembled a few years ago. So these supercomputers also require a lot of cooling in order to, and the cooling to be dissipated. But they also, of course, they are very useful. Here is an animation of an output from a high resolution climate model is Hawley water vapor. And you see that if you compare this with the satellite images, I think we will not be able to distinguish which is what. This is super high resolution, is super realistic. You see the formation of cyclones in the mid-latitudes, you see the ITCZ, and so the monsoon propagating northward, and so on. So it's really, really realistic. But of course, at such a detail, we can run the models only for a limited amount of time. Yet models are not perfect, even from the point of view of the equations, because we cannot simulate all processes that exist in the atmosphere, simply because some processes occur at time and spatial scales which cannot be resolved by these grid boxes. And this is typically the case, for example, of clouds. Clouds involve, if you see a satellite picture of a cloud, you see a lot of features. And that if you think of the grid box of a model, typically 10, 20, 30 kilometers, you know that within this grid box, there can be multiple clouds in reality. Sorry. And also in the vertical, you see a cloud involves an updraft, involves also a downdraft. You know, in a cumulonimbus clouds, we have a strong downdraft. You have entrainment of air from the environment. You have various small-scale processes. All these processes cannot be represented in a model because the model have grid boxes that are much larger than the one involved here. Another example is turbulence that occur on time scale of millimeters. And of course, you have large-scale mixing, but ultimately the mixing depends on mixing a very small scale. And a model, again, cannot resolve this mixing, if not for the temporal scale at which this occurred. And the fact that, so models include the so-called parameterizations, which are representation of these phenomena based on large-scale values, grid-scale values. And we talked about the atmosphere, the ocean, the land. I mentioned about the land model. And a land model, in principle, for a state-of-the-art Earth system model includes various components. The component associated with the energy budget, and you see here, you don't need to go through these details, but you see the arrows represent the processes and exchanges that occur. We have water, of course, hydrology through plants, evaporation, moisture in the soil, and then we have the carbon cycle. And what's important here is that these processes are all coupled. We know evaporation releases moisture from the surface to the atmosphere, but at the same time cools the Earth, and because some heat is being lost in the atmosphere, and so on. So these processes are coupled. And so a land model includes a lot of interaction among these whole processes. Regarding models, you might think, okay, we can decrease the resolution. And indeed, this is done. There are different categories of models. Some are represented here. And from the global scale, as I mentioned, GCMs, global circulation models, to smaller scale, for example, parcel models or large eddy simulations, which are basically models that are typically also 1D. They resolve the atmosphere very finely in one dimension. But of course, again, we can run this type of models, but we cannot run them all at once. Okay. And in terms of climate, we can downscale global models to run at higher resolution, but on a smaller domain. These are called regional climate models. They take boundary conditions. You need boundary conditions in order to have the flow of energy, wind, and so on at the boundary. And then you resolve the equation on an inner domain, but at higher resolution. These are typically used for impact studies, as indeed the climate is resolved at higher resolution under boundary conditions. So if you want to do projections with regional climate models, you still need global models to run, though. in order to have the large-scale boundary conditions. And this is done as part of the CORDEX framework, the Coordinated Regional Downscaling Experiment, where multiple regional climate models are run over multiple domains with multiple scenarios and driven by multiple general circulation models. But is this the solution? They still differ. And this is a plot showing the distribution of climate regimes over the US. On the left are the driving general circulation models. And then we have different regional models using the same boundary conditions. If you move horizontally, you see different models using the same global model. Different regional climate models can differ quite a lot. If you look at the middle rows, they differ quite a lot while having the same global model. And interestingly, both regional models actually differ significantly from the driving global model. You can also see this in the other way. So looking at the same regional model driven by different global models, and you also see differences here. So there are a lot of things to consider when we examine regional models and global models. Global models, as I mentioned, you developed substantially, especially when the first models were developed. Then more and more components were added to the model. And this is just showing the advancement in resolution. So and together with the IPCC style initiative, so FAR on the left-hand side stands for first assessment report of the IPCC, SAR second, third, and so on. We moved down as time passed. So you see resolution changed. We moved from 500 kilometers to 30 kilometers in the fifth assessment report, which is now the sixth has been completed a few years ago. And also more components have been added. And as you see here, the first models were just including few components, then the ocean, a mixed layer ocean was added. Then the full oceanic model was added full oceanic in the early 2000s. And then chemistry, and then the full carbon cycle. These are essentially the milestones in climate modeling. And you see here as well, with the key components that were added in various phases. So the carbon cycle, primitive carbon cycle was added in the early 2000s, and this is quite important. Chemistry was added in the late 1990s with aerosol science and so on. Okay. And you can see, you can focus here on the part that you are more interested into. And as I mentioned you before, a system model closes the carbon cycle with ocean ecology and biogeochemistry, ecology and then use over plants, and interactive CO2 in the atmosphere. And this is what the state-of-the-art ESM incorporates now, this whole range of processes in the atmosphere, ocean, over the land, and over the cryosphere. I haven't mentioned the cryosphere, but that's important too, obviously. So we can go through this, but there is no time, obviously, to talk about all these processes here. But just to give an idea of the complexity of these models and the fact that these components are all interactive and solved almost simultaneously at each time step. And to move forward, climate modeling, climate models and projections are made by using driven climate models by emission scenarios. And these are the latest scenarios that were developed for CMIP 6, so Climate Model Intercomparison 6, and the latest assessment of the IPCC. And they're called shared socioeconomic pathways. What I want to point out here is that these, for the first time, were developed by accounting for developments in societies, in populations, in distribution of technologies, rather than prescribing a certain forcing. So these account for how society will develop, how technologies will be implemented. And there are essentially many of them, but there are essentially 5. And they are depicted here in terms of challenges that each of them requires to adapt to climate, to socioeconomic challenges, as well as challenges for mitigating the effect of climate. The worst one is SSP5, which has very low challenges for adaptation in the sense society will develop as business as usual, so we don't adapt. But there will be a lot to mitigate the effect of climate change because climate will occur very substantially. And they differ then by the amount of CO2 being emitted. As you see, the SSP5, which leads to a forcing, so the imbalance of radiation at the top of the atmosphere by 2100 of the range of 8.5 watts per meter square, to the other more optimistic SSP126. SSP1 is the more optimistic, and which will also see a decrease in CO2 emissions. But also we talk often about CO2, but we also have to account for aerosols, just to point this out. And we can talk about this again extensively. And it's interesting to see how model efforts developed across the most recent CMIP type experiments. In CMIP 6, this is a typo here, is CMIP 6, there were 49 modeling centers with 100 more different models. And this followed the ability of computers, the power of computers, and the type of simulations that are being performed are more and more complex. And we started in 50, 60 years ago with running month-long simulations, perpetual summer and winter type simulations, with the annual cycle, the full annual cycle added only more later. And these were only atmosphere-only models, to nowadays, the frontier of climate modeling and climate projections encompasses large and grand ensembles of realizations. We will see in a moment what it means. And this is the type of experiments carried out as part of CMIP 6, a full range of experiments looking at specific aspects of climate. This is just to give you an idea of the range of experiments, MIPS, the Model Intercomparison Project, they were designed and carried out as part of CMIP 6. The complexity essentially have increased and honestly is almost unmanageable. Even for scientists doing science actually becomes almost unmanageable. And we know climate models have been used to attribute climate change and to see and to quantify the causes of climate change. And this is one of the pictures of the diagrams made by the IPCC. So how do we actually the observed warming up to in the period 1951 to 2010 and the causes of that warming with the bars of uncertainty as well. And you see most of the warming is attributable to greenhouse gases, with aerosols, other forcings here is mostly aerosols contributing to cooling the planet. And this is more a refined picture with actually, you see much of the warming coming from greenhouse gases is actually attributable to carbon dioxide and methane. And the cooling due to aerosols is almost attributable to sulfur dioxide. And again, we can discuss about this, but the point that I want to make is how do we do this? We run the model with different forcings, with our various combinations of forcing. Having a model is useful because we can switch on, switch off various combinations of forcings. We run the model and we see what happens. And this is essentially what's done. You see here, however, there is a range here. The range here is because of different models, but not only, also because we need to run ensembles of realizations with a certain model to sample the variability in the atmosphere and in the ocean and so on in the climate system. And indeed, internal variability represents, there are uncertainties due to model variability, but internal variability represents a large source of uncertainty in climate, especially in the short term. And why is so? Because the climate involves a number of feedback processes. What is a feedback? If we impose a certain forcing, the climate will respond. But the response will also affect how the forcing is being translated to the climate system, because changes in climate translate into changes in temperature, but changes in temperature also translate back in how the forcing is being exerted on climate. And so we have all this interactive loop, which is feedbacks, and thus this makes actually the warming much more severe. We can calculate that doubling CO2 will result in a 1 degree warming if there were no feedbacks. The fact that actually the climate will warm by 3-4 degrees, doubling CO2, is because of these climate feedbacks. Some of them are listed here. The ice albedo feedback is perhaps the most known one. If we reduce ice, we have more oceanic surface, which is darker, which will warm more, which will lead to further ice melting and then more warming and so on. So essentially, given a certain amount of forcing, the warming will exponentially amplify. And a similar feedback involves water vapor. So if we increase the warming, there will be more water vapor in the atmosphere, more humidity. Humidity reduces the amount of emission from the planet of long-wave radiation, and thus the climate will warm even more. And so these are positive feedbacks. Of course, there are also some negative feedbacks, but in general, these are positive. And some of the feedbacks, the lapse rate feedbacks, and so on, are depicted here. I want to make the final point here on internal variability. Internal variability, like the one depicted here because of ENSO, can affect how we perceive climate change, how we attribute climate variations to a certain driver or certain forcing. This is the example of ENSO, and you see here in the global mean surface air temperature, the imprint of the El Niño Southern Oscillation, and the fact that if we compute trends or changes temperature over a limited amount of time, we can lead to conclusions that are wrong. The same here. This is a long-term simulation with a state-of-the-art climate model represented ENSO. ENSO time series over 2,000 years, a climate model run at equilibrium over 2,000 years. We don't need to go into this detail here. Just simply notice how, if we look at different segments of the climate simulations, we can have different periodicity of ENSOs. So this goes back to what I was showing you before. How maybe ENSO, this is only due to internal variability, chaotic variability in the climate system. The fact that even if the model is the same, run at equilibrium, nothing changes. The periodicity, so the variability in the model can change substantially from, if we look at a 50 year in a certain amount of time and 50 years over in a different time period within the same climate simulation. Is very different. And you see, comparing the colored pictures. This is why we need to run multiple ensembles. And this is a depiction of what I mean by running multiple ensembles. The picture on the right represents trends simulated by a climate model of surface temperature over North America, over 50-year trends. Different realization from the same climate models. The colors represent different ensemble members. The bottom right is observations, and EM stands for ensemble mean. So the mean of these realizations, so we can say that the model as a whole captures observations relatively well, but if we just run the model once or twice, we can have trends that are actually opposite to observation, even opposite to observation, or maybe we get cooling instead of warming, just simply because of internal variability of the model. I think I need to wrap up here. There were a couple of other slides talking about models biases, and models have bias. We acknowledge that, we know that, and in a way is known simply because of these feedbacks and because not all processes are represented in the models. And I conclude with these few points. We can go back to the biases if you're interested in a Q&A. So as we saw, models are basically running on established physical laws, although there are parameterizations, and models are able to simulate important aspects of current and past climate. We are aware, as climate community, as some climate modeling communities, there are uncertainties. Clouds is the key uncertainty in climate modeling. Regional climate change and variability is also not extremely well simulated as well as validated. Aerosol effects also are highly uncertain, and we know aerosols contribute to offsetting part of the greenhouse gas warming. And the oceanic response is not known very well as well, because it occurs on timescales of 50, 100 years, and we don't have observations of the ocean here on the Atlantic for more than a few decades. And plus, as I mentioned you before, climate variability, internal climate variability, such that associated with the North Atlantic oscillations, can alter or can offset externally driven climate patterns over a certain amount of time and spatial scales. And the final point is that we don't know the climate very well. We cannot observe the climate very well either, I must say. This is a time series of Indian rainfall measured by stations observations. And you might expect divergence across the station observations, different data sets in the early century, in last century, not now. As you see here, if we want to attribute or want to study changes in the monsoon in the last 30, 40 years, if you see different data sets would give different results. One data set, the black line, would say that the monsoon has decreased. Another data set, the red one, will show conversely, perhaps a large increase in the last 30, 40 years. And so these are station-based observations. I think I conclude here. I'm happy to receive questions if there are. Thank you.
Thank you very much for your talk. Very interesting stuff there. We'll welcome questions. I noticed there's two on here, but I'm going to kick off while people are thinking about things. You started off with some discussion of both the history of weather models and climate models. And what are the key differences between forecasting the weather, which we do over a timescale of about 1 week, and forecasting the climate for 100 years? What's the difference in the model process there?
The models are essentially the same. They have differences in some processes. For example, we don't need to include sophisticated features of carbon cycle in NWP, because we can also assume that CO2 in the atmosphere is constant over a time scale of 1 week or 2 weeks or so. So we don't need, for example, these facets in climate models. Resolution is likely larger. For example, ECMWF runs 50 ensemble members, while climate models are not run in general with 50 ensemble members. Also, an NWP depends strongly, it has as a backbone a very reliable data simulation system, while climate models run, they don't need this data simulation. They start with initial conditions, sometimes with so-called cold start from a previous model, and they need to be spin up in order to reach an equilibrium climate, and then simulations are being run on top of this. So the models in general include similar processes, are the same, similar parameterization, similar implementations. Simply is how the simulation is being configured that differs a lot between NWP and climate modeling.
Right, thank you. I'll ask one more question and then pass on to the ones being written on the question and answer. How do you establish confidence in climate models? You're predicting for 100 years ahead. With a weather model, you can wait for the 1 week and see what happens, but we're trying to, we don't have that option with climate modeling.
Yes, that's true. How do we do? we typically validate a climate model with observations. We first examine whether the model is able to reproduce changes in climate that have occurred and have been observed, mostly observed over the last century, very likely over the last 50 years or so, when observations are more diffuse, especially satellite measurements. So we compare the model simulations and we sort of tune the model in order to be able to represent these observed phenomena and features. And then, based on this, we assume that the model will be able, will realistically, if the model is realistic in simulating present-day climate, will be realistic in simulating future climate. We assume that, which is quite, it's an assumption. Assuming, in a way, assumes that climate features in per se are stationary, which assume you know what I mean. It's an assumption. It's a solid assumption. It could be that climate will transition to a completely different state, and some things might not occur completely in the future climate, which then, of course, models that have been in a way tuned, and here in quote unquote, to represent present-day climate, what might not represent future climate.
Thank you. I'll just look at some of the questions on the screen here. Yeah, one from Len here. Surely there are diminishing returns in increasing resolution just because you can with faster computers when the science involved with feedbacks and so on doesn't keep up. And the evolution of clouds, for example.
Yes.
Is this an issue that people see?
Yes, we know. Unfortunately, yes, resolution has gone up quite a lot, but clouds are still a key uncertainty in climate modeling. And so, I must say, some models have been showing biases in representing critical phenomena in climate since over the last 20, 30, 40 years. And despite this is not saying that we scientists sit on our desk and we don't work. It's simply saying that there are some intrinsic limitations in our understanding of how the climate works and how we can implement these in models. And so, yes, it's still very challenging.
Just to follow that one, the climate evolution, there's something that has been sort of an observation that you see is particularly in the tropics, is you get diurnal variation of the cloud. So you start off, it's bright and sunny in the morning, and then the cloud builds up through the day. Do the climate models account for this? Because the feedback from that will vary according to what kind of area it is and all kinds of things. Yeah.
Yes, this is another good question. Yes, clouds. We talked about cloud briefly before. Yes, it's quite a challenging area of research and limited. If we want to call it weakness in models, the diurnal cycle is another one, with models tending to represent the development of convection slightly out of phase compared to observations. Climate models have this because the equations I didn't mention, but the time step implemented in models for the equations is something like 10 minutes or something like this. It's of the order of minutes. So the model knows about the state of the atmosphere every few minutes. Okay, so that means that includes the diurnal cycle. Then, of course, convection is another challenge, and it's known that models then, particularly over some areas like maritime continent, where we also have orography and so on, the development of clouds is not in phase with observations. Yes.
Okay, I've got a question here from Ioana Colfescu, who gave us a talk about a year ago. What do you think will be the main progress the new AI and ML, I think that's artificial intelligence and machine learning approaches, will bring in the model progress, addressing some of the weather and climate uncertainties? On the contrary, do you think there are any concerns or weaknesses that AI methodologies might bring to the traditional dynamical weather forecasts?
This is a very challenging question. Yes, I think I see the use of machine learning and AI in a way very positively in our area. I would say so, helping to solve some of the problems, absolutely, in using less time, and thus enabling us to run a certain model or to run projections more quickly. Yes, this is the state of the art where we're going. The contrary, do you think there are any concerns on or weaknesses might bring to the traditional dynamical weather forecast point of view? Well, weaknesses is that some of these, all of these codes are not really black boxes. So we don't really, it's not based on physical principles. It's just numerical algorithms. So of course, the model can run faster, but at the same time, we'll not know much about what happens within that machine learning code or AI code. In a way, I think from the point of view, they need to be used, still keeping in mind the physical understanding, I think.
Okay, thank you. I've got one final question from Rizlan. Just to paraphrase it, how can you choose the best regional climate model for a particular place? Is there some way of categorizing the models?
For a regional model or global model used at regional scale?
I don't know.
Both of them. Well, we use as many observations as possible to validate the model based on present day climate. This is what we do all the time. So doing first a validation of the model for the specific phenomenon that we are studying over a certain region, and making sure that the model captures the key aspects of distribution, patterns, temporal variability of the certain features that we are investigating. And then we can then assume that the model is okay to be used for projections.
Okay, thank you. Have we got any more? Oh, yeah, yes, sorry. What do models have to say about the warming and melting tundra, the release of methane and warming feedback? Is this now unstoppable feedback reaction? This is basically in the Arctic or polar region.
Yes, yes. Well, if it is unstoppable or not depends, I would say, on our ability to stop emitting CO2, and actually not just stop emitting CO2, but actually removing CO2 from the atmosphere. Because we know even if we stop the emissions of CO2, the climate will still warm because of the fact that warming associated with what we have emitted so far has not been realized fully. So CO2 will still remain in the atmosphere and will still warm. It's not a gas that is being removed, will be removed quickly. So that said, this feedback, what will happen will depend on us whether we are going to remove CO2 from the greenhouse gases from the atmosphere. My view is very pessimistic, and so we can. For me, yes. I cannot say it's unstoppable. I can only say my view is very pessimistic. on what how climate has been evolved in the last 30, 40 years, observing and studying. And so I see that warming will be quite high in my view, and that feedback certainly contributes to. We have seen every year the Arctic ice is going to a new minimum compared to the now 40-year climatology or even internal variability. So in that sense, I think we have been reading recently, right, of the possibility for the AMOC to stop or to reach a certain change in the coming 20 years or so. Essentially, scientists saying that now there is a high probability for that to occur in the coming 2 decades or so. And that is also associated with the Arctic warming and so on. So they are all essentially related.
Okay, thank you very much. I think that's all the questions we have. And so it remains to me to thank you very much as the speaker. We would have a round of applause if anyone could hear it, but I'll make mine. And I just have 1 or 2 slides to close with, just addressing the audience now. If you're interested in the society, there's this free newsletter called Met Matters, which you can sign up for. And then if you're even more interested in the society, you can join, which will cost you money. You can get all the details on this website, www.rmets.org. And that will give you lots of further information. So once again, thank you very much, Massimo. That was very interesting talk, very detailed.
Thank you.
Of information.
Of course, I must say, if any in the audience is interested in, feel free to get in touch with me by email.
Yes, and if you want to look at the talk again, it's been recorded, so it will be up on the Society website in a few weeks, a couple of weeks, I think. So thank you very much once again. I'm going to close the meeting, and we wish you all the best. Take care. Bye.